Linear span is nothing but set of all linear combinations of the given vectors in that set. So let me write linear span of S, assuming S equal to V1, V2, and so on Vn, right? So the linear span is set of all linear combinations of these vectors, where alpha belongs to field and I is running from 1 to up to n. Now my question is this linear span a vector space? Why? Because it is a subset of V only. Let's assume that this S is a subset of a vector space V, and then if you take a linear combination of these vectors, definitely that belongs to big V. Why? Because V is a vector space. So it is very clear that LS of S, that is linear span of S, is a subset of V. Okay. Now my question is this a subspace? Is linear span of S a subspace? So if you take any element in this linear span, that can be expressed as a linear combination of these vectors. For example, let me assume U is an element of linear span of S. It means that there exists some alpha I. It means there exists some alpha 1, alpha 2, and so on alpha n, such that this U can be expressed as alpha 1 V1 plus alpha 2 V2 plus and so on plus alpha n Vn. Now let me take one more element from the same set, from the linear span. Let me name it as V. Let me assume V belongs to linear span of S. Since I already used these alpha ones for U, so let me use beta ones now. There exists beta 1, beta 2, and so on beta n from the scalar set, that is field, such that this V can be expressed as beta 1 V1 plus beta 2 V2 plus and so on plus beta n Vn, right? Now if I can prove that U plus alpha into V, if this is an element of linear span, then we can say that this linear span is a vector space. Moreover, it is a subspace of V. Okay, so let me see that. So now let me add U plus alpha into V. So that is nothing but I'm writing it directly. Okay, so this is alpha 1 plus alpha into beta 1 into V1 plus alpha 2 plus alpha into beta 2 into V2 plus and so on plus alpha n plus alpha into beta n into Vn, right? So now this U plus alpha V, this is also a linear combination of Vi's only. So if it is a linear combination of Vi's, see, alpha 1 is a constant, alpha is a constant, beta 1 is a constant. So now totally this entire expression is a constant. So I can take k1 here, k1 v1 plus k2 v2, where this k1 I mean alpha 1 plus alpha beta 1 plus and so on plus kn vn. So definitely it belongs to the linear span of S. So therefore the conclusion is linear span of S is a subspace. Is a subspace of V over F. So now the beautiful thing is that if you take some finite number of vectors, whether it is finite or infinite, it can be anything, but we proved it for finite only. Similarly, you can generalize this result for infinite case also, right? So the linear span of any set, you can say that that forms a vector space. So linear span gives you a vector space. Now let me take a set S equal to 1 comma 2 comma 1 and 3 comma 1 comma 0. Now my interest is to see what is the linear span of S. What is the linear span of S? See, definitely the linear span of S will give you a subspace. A subspace of what? Since it is a subset of R3, so it will generate a subspace of R3. Okay, and we know what are the subspaces of R3. They can be 0, that is a singleton set which contains 0 vector only, or they can be lines passing through origin, and the other are planes passing through origin, and the next one is entire R3. These are the possible subspaces for R3. Okay, so now let us see, these two elements are either the generating a line or a plane. Let us try to see that. And if it is generating a plane, let us try to see what is the equation of that plane. Okay, so for that we need to find what is the linear span of S. So let me go for it. So this is nothing but set of all linear combinations of these two. So let me write alpha 1. Let me use alpha beta. Okay, alpha into 1 2 1 plus beta into 3 1 0, such that alpha comma beta, these are coming from real numbers. Now every element in the linear span looks like this: alpha plus 3 beta. I'm adding it directly. Okay, so 2 alpha plus beta comma alpha plus 0 into beta, such that alpha beta belongs to real numbers. Okay, so now this is the space generated by these two vectors, or this is the linear span of 1 2 1 and 3 1 0, or in other words we say that it is the space generated by these two vectors. Why? Because with the help of these two vectors only we got this space. And let us try to see what is this space, what does it represent, is it a line or a plane? Okay, to see that, I'd like to do one thing. I'd like to compare this element with an element in R3. What I mean, so let me assume this set is same as, so this is equal to set of all x comma y comma z in R3, the condition satisfied by x y z that we need to write here. So we got alpha and beta, and we have one more equation here, the middle equation, right? So you substitute this alpha and beta in this equation. So if I substitute it here, so let me keep it here. So now y equal to 2 times of alpha, that is z, plus beta is nothing but x minus z by 3. So this implies you get 3y equal to 6z plus x minus z. So from this you can clearly see it is nothing but x plus 5z minus 3y equal to 0. Now this is the plane equation. Now if you observe that every point which belongs to this linear span satisfies this equation. That equation is x plus 5z minus 3y equal to 0. Now every point on this linear span can be represented with a set that is xyz belongs to R3 in such a way that x minus 3y plus 5z equal to 0. Right? So now if you observe that these two vectors are generating a plane, and the plane equation is given by x minus 3y plus 5z equal to 0. So now if you ask me whether 1 comma 2 comma 7, whether does it belongs to this linear span or not. Now what do? Simply substitute this point in this plane equation. If it is there on the plane, then I can say it is there in this linear span. Otherwise it is not. Okay, so let me keep it here. 1 minus 3 times 2 plus 5 times 7, which is anyway non-zero, therefore which doesn't belongs to the linear span of S. Now I have one more question. S equal to 1 minus x, 1 plus x square, and one more, that is just 1, which is a subset of P2, set of all polynomials of degree less than or equal to 2. Now, can you tell me what is the linear span of S? Now we want to find linear span. Let's try to write the linear combination, that is alpha 1 into 1 minus x plus alpha 2 into 1 plus x square plus alpha 3, where this alpha 1, alpha 2, alpha 3, these are coming from real numbers. Now you try to see what is the constant term here, that is alpha 1 plus alpha 2 plus alpha 3. This is the constant term plus the coefficient of x, negative alpha 1 plus 0, there is nothing, into x plus, and the coefficient of x square, that is only alpha 2, so alpha 2 into x square. Okay, so where alpha 1, alpha 2, alpha 3 are coming from real numbers. You know this is a subset of P2. So every element in P2 can be expressed as set of all a plus bx plus cx square. This is how every element in P2 can be expressed, where a, b, c are coming from real numbers. Okay. Now, like earlier, I am going to compare these terms here. So if you compare, so the first thing you're going to see a equal to alpha 1 plus alpha 2 plus alpha 3, and b equal to negative alpha 1, and c equal to alpha 2. You just compare the coefficients. Okay, so last two equations gives what is alpha 1 and alpha 2. So from this, alpha 1 is nothing but minus b, and you can see what is alpha 2. So alpha 2 is c. Now from this equation, you can actually see what is alpha 3. Now alpha 3 is nothing but all right. So now the alpha 3 is so this is a minus alpha 1. Alpha 1, you know, that is minus b, so a plus b, all right, minus alpha 2, that is c. Now, do you get any relation between a, b, c here? We are just saying that alpha 1 you take minus b, and alpha 2 you take c, alpha 3 you take a plus b minus c. And we didn't fix ABC here. ABC, they can be any real numbers. Okay. So C can be any arbitrary real number. B can be any arbitrary real number. And similarly, A plus B minus C, that can be any arbitrary real number. So here, if you observe that, we didn't really get any condition between A, B, C. So A, B, C are not satisfying any condition here. So it means that you're allowed to choose any A, B, C, right? It means that the linear span is nothing but entire P2. Because there is no relation between ABC. ABC can be any arbitrary numbers. So therefore, the conclusion is the linear span of S is nothing but P2. It generates the whole space. These three vectors are generating the entire polynomial space. I mean, polynomials of degree less than or equal to 2. Okay, so this is how you can find linear span.